Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to have Suman Banerjee here to give us a talk. Suman got his PhD degree from University of Maryland, and now I just learned he become associate professor. Just get his 10 days back. Sorry, and he's going to talk about his wing lab, Wisconsin Wireless Networking System Laboratories. Surely is a very interesting name. And let's hear what Suman has to say.
So thanks, Jin. Thanks for inviting me here, and it's a great pleasure to be back. When I'm coming here to give a talk, I need to make sure I get to say something new. I've been here multiple times in the recent past, and I've talked about certain things, but thankfully over the last year and a half, we had a lot of interesting activities, and I'll try to cover some of them. Getting through all of them, of course, in this time wouldn't be feasible. And this logo of our lab is actually designed by one of our grad students who was an intern here, Vladimir. So very good in artwork. Highly recommend him for any logo design for any new conference or workshop that you may have in mind. Although we have a newer version of that logo.
That just sounds bad.
That's okay. No, he's pretty good. In research as well. Yeah. So anyway, so what I want to talk today about is a theme I think everybody here already subscribes to, so it wouldn't need a lot of motivation. But basically, I'm going to focus on building robust wireless network services through infrastructure support. Previously, we did a lot of work focusing on the client-supported services where you kind of install specific things in the clients. Today, I'll focus on infrastructure support for a set of specific services, specifically targeting enterprise wireless environments, but some of the ideas, of course, apply to fairly generic 802.11-like wireless environments. So just a quick run through the initial motivation. Any enterprise would like to tightly control all of their resources, which includes, of course, office space, network bandwidth, applications, devices, and definitely the wireless spectrum. So as we all know, wireless spectrum is a challenging thing to really control because it's a shared resource. The spectrum doesn't respect building perimeters, so you may have intruders who are located outside the building who can easily kind of extract signal out of transmitters inside the building, which becomes a major pain point for many IT administrators. Yes?
Do you know of cases where IT admins have actually worried or actually detected such intrusion? Like, I see a lot of work being motivated by such a scenario, but I haven't come across any incident.
Yes, that's a very good question. I think it's a kind of a fear factor, I guess, for more of the financial institutions I hear. Like, if you go and, for example, talk to Cisco, they will say that this is a capability that their customers worry about. Who the specific customers, I don't exactly know. I don't think most university campuses or even regular, campuses like Microsoft would worry that much about it, but they seem to worry about it. They seem to feel that, we need to make sure this is true, but I don't know. I don't have a very good answer to that. I wish I did.
I recall once, there's a talk by Boeing who talked about Boeing's infrastructure. And their current thinking that they don't trust any device connected to the network.
They're including their own.
Including their own.
Sure.
So basically it means, plugging into this jacket doesn't mean your device belongs to the network.
Sure.
It depends on other layers.
That's opposite of what this worry is, right? That makes sense.
Right. That's a very different attacker.
Right. So I think his question is whether somebody just eavesdropping, sitting outside the building, is that a real threat? Parking lot-like attacks is what basically people worry about. There are examples of incidents which are, I think there was the Mumbai bomb blast of last year, and it seemed that the perpetrators actually had sent out emails by hijacking somebody else's Wi-Fi. Now, you could think of, that somebody outside the building is actually hacking into your network. So that is, You're not eavesdropping, you're accessing the network. So if you knew that this person was physically not present inside the house, I would not let his signal inside.
But that just seems like a failure of cryptography rather than...
True, but there is issues with crypto too. I mean, you have to configure, people have higher... If you had a simple way of saying, okay, the signal doesn't go out, or you cannot penetrate from the outside, or I can detect outsiders easily, then...
But here's the thing, right? I mean, that's always a function of how powerful an antenna I have.
Sure. Well,
there is no such thing as signal doesn't penetrate.
True, but even if you could figure out, you have a strong antenna or sensitive antenna, and you can get in. If I can somehow localize you, I could still try to prevent you from getting in, I guess. Okay, it's not a very strong example. I'm not trying to claim I have an answer to that. But nevertheless, these are the different scenarios that I will try to focus on. So again, this is something very well understood here. Early on, we had enterprise wireless LANs, which were very distributed in nature, and effectively, each access point was asked to fend for itself. So everybody fought for their own channel access. They decided their own channels to use, AP client association mechanisms, PHY rates, and all of that. And today, we are moving towards a much more organized structure where it's almost like a legion where there is a controller that manages all its soldiers or all its access points and decides a bunch of parameters for these access points, which makes things a lot more streamlined. Okay, so within this framework, what I'll try to focus on is how this approach can be utilized for a few specific solutions that we have looked at. So one of the things that I'll talk about is achieving high throughput through data path centralization. And I think that's a very interesting question in itself, that a lot of the control mechanisms like channel assignment, load balancing, and a bunch of other parameters have been centralized. But the key decision of whether, how, or when you access the channel, can you centralize that? Can you take the decision in the controller? That's one question we'll try to look at. And of course, it will be based on some kind of scheduling mechanism. So we'll look at that. Then I'll look at energy efficiency, and we'll look at some techniques on which a controller can facilitate the mobile devices to be energy efficient by specific mechanisms. Then I'll talk about some rich media services. This will be a very short part of my talk towards the end, how the infrastructure can facilitate improved media services in the environment. And finally, I'll talk about security capabilities leveraging the infrastructure. Okay. So let me get started with the first question, which is,
I get a sense of like, in doing this, what are you willing to change and what are you not willing to change?
So yeah, that's a good question. So the question is, what do we want to change when we try to implement some of these services? Ideally, our goal here was to do most of the things only in the enterprise, so that you can come in with any arbitrary client. You don't need to go and physically modify all the clients. But in some cases, you cannot do that, and you have to make changes on both sides. So there are advantages of doing changes only in one side of the environment.
Yeah, but I also meant like in terms of like hardware, firmware, software, and all those changes.
Right. So almost everything I'll talk about can be built on 802.11 without making any changes to the standard. So I'll answer this question individually for each component. So we don't have a unified strategy for everything. So in some cases, because of what gains we get, it might make sense to do more, maybe make firmware level changes. In some cases, we can live with only simple driver level changes at access points or at clients.
So you can say after the fact, after the design, what you need to change and what not. I'm trying to get a sense of like, as you approach the problem itself, like did you place constraints on yourself?
Yes. So we did place, and again, I'm kind of integrating different pieces of work. So it's not going to be a consistent answer every time. If we constrain it in a certain uniform way, in some cases, the amount of gains you can get reduced. And obviously, more changes you can make, the better you can do. So there is a trade-off. And so the first one, I'll let me kind of take the first one as an interesting example, where the goal is to kind of do scheduling or accessing the medium in a centralized way, and our goal there was to not change the 802.11 standard at all, but provide a little bit of a simple API from the access point by which we could manage the spectrum and not change the clients at all.
I would just kind of follow up on the discussion a little bit more.
Yeah.
We looked at this in I sent you the paper yesterday.
Sure,
so,
yeah.
The SIGCOMM paper and the density paper. Here's the thing. It's a matter of where to draw the line.
Mm-hmm.
I mean, it's not so much a matter of whether you want to change the API of the client, although that's the main distinction in terms of deployability.
Right.
But after that, I mean, you have to think about whether you want to keep the CSMA MAC, right?
Sure.
I mean, if you're in an enterprise environment and you have full control, why do you even want to keep the CSMA MAC? There are all these papers that say TDMA MAC is so much more efficient, and
that's exactly what this work was motivated by, and I think that you need to keep the CSMA MAC to some extent because you have to coexist with others. Even though it's an enterprise environment, we don't want to change the clients, which means the clients are going to use CSMA MAC. So you have to coexist with that. And you may have non-enterprise traffic, which is maybe peer-to-peer traffic for some specific applications. So you have to coexist with all of that. So if you could change the clients and say, I'll have a TDMA MAC across everything, then sure, you can change the CSMA MAC. But here we will not try to change that. Okay. So this is the question. So we really kind of saw a bunch of papers, mostly I guess simulation based, which showed that if you could do a very good scheduling, of course you get this very nice efficiency. So is there a real role for centralized scheduling in enterprise wireless LANs? And if you think of a distributed multi-hop wireless environment, one of the challenges is if you want to build a schedule of traffic across all of these nodes, you need to really know who has what traffic to send and when. Okay? Which means you have to aggregate all this information in a central point, which means there is overheads in aggregating all this information. And what we will really try to leverage is that the enterprise has a nice structure that can allow us to get this information for a lot of the traffic for free. And that's what we'll try to leverage in this work. Okay, so let's look at this with a very simple example. So here is a very simple enterprise network with 2 access points, a few clients, and we have an edge router. We assume that all the traffic that is downlink in nature goes through this particular edge router. Okay, and what happens is, let's say these 2 access points happen to be hidden terminals to each other. That means the access points cannot sense each other, but the clients will of course get interfered with each other if the 2 access points transmit together. And now let's imagine there is a red packet and a green packet intended for these 2 clients, red and green. And typically in the DCF mode, what will happen is these 2 packets will get sent to the different access points without any special mechanism in the router. And then eventually the access points will do a carrier sensing act. They will not sense anything, and then they will transmit. They'll sense the channel to be free, and they'll transmit. And that will lead to collisions, backoffs, low throughputs, all of that happen. So hidden terminals are a very known problem in this setting. Now, how can we, so why is this an important problem? So some people feel that, okay, hidden terminals, maybe do they occur once in a while? Is it an important problem? Do we really care about hidden terminals? If you really went ahead and did a very nice placement of access points in the enterprise, maybe you can eliminate all possible hidden terminals, right? But if you really look at the picture here before, the reason we had this hidden terminal was because of the location of the clients. It is not because how you place the access points. So clients can show up somewhere, and they create the hidden terminal with respect to the access points, and you cannot avoid it. Okay, so there is a reason to believe that hidden terminals may occur even if you had the best assignment of channels and the best assignment of location of access points.
Are you assuming in your argument anything about like the spatial distribution of clients? Like if I look at enterprises, like clients tend to, like stationary clients tend to cluster in specific places.
Sure.
Like lounges, conference areas and whatnot. So
Certainly.
it's unclear that your argument actually would hold in that setting.
So I'll give you some numbers. These are, so here some measurements we did were from an office building like here, where you have clients sitting in each office and working on their laptops. And yes, you can have, even if you're sitting in lounges and maybe in conference rooms, if you are unlucky and 2 people connect to different access points, you can easily have a hidden terminal scenario. If you are...
most places where you hear 2 access points, they are not on the same channel.
Well, I'll give you examples, and these are real measurements. Okay, I'm not, let me explain this plot first. Okay, so what we did was these were using regular production enterprise wireless LAN. One happens to be, of course, in our CS building in Wisconsin, and the other is in Waterloo, University of Waterloo. And the 2 production networks are very different from each other. Ours is a Cisco-based network. They're all manually deployed. The IT administrators went and figured out where to place the access points. They manually assigned all the channels. We had 9 access points in our in the 5 floors that we are considering actually, and they did channel assignment. Okay, the Waterloo network is actually Aruba network, and Aruba has a lot more sophisticated algorithm. They actually have a little more denser architecture. They place more APs in the environment, and they have a dynamic channel assignment scheme. So they're always changing their channels. Okay, and then what we did, so we didn't change anything in the network. We went and basically placed our nodes in different rooms as if they were like people sitting at different desks. Okay, and then what we did was we allowed these different clients to do pairwise tests and see what the throughput impact is. Okay, so this plot, what it shows, so on the x-axis you have a bunch of AP client links. We had about 45 and 51 clients in the 2 networks. And let me see here. Oh, I think, yeah, this is fine. So basically what this plot shows is the reduction in throughput that happens when the 2 links went together compared to when the links went in isolation. Okay, so if your reduction is 0.5, it means that you just equally share the channel. That's perfect, right? If you're in isolation versus you're sharing it with somebody, you get half the throughput. That's what we would expect. Modulo, data rate, and all those things. Now, if you go significantly below 0.5, that's a kind of a hint that there is hidden terminal interference happening that you are not able to control. And so what we found was that a reasonable, so throughput reduction, so above 0.5 is hidden terminal. Below 0.5 is not hidden terminal. Okay? Below 0.5 actually means that you're not really interfering, so that's why your reduction is almost 0. Okay? So we had about a third of our client AP pairs, or a third of our client AP links had a hidden terminal from another client, and some of them went up as high as close to almost 0 throughput. Okay? So it's anecdotal evidence from 2 networks, but it at least shows that you cannot plan things accurately, because even if you have 2 weak access points and some clients placed and connected to these channels, you're just hosed. You cannot do anything. And even though I would, you could argue that, okay, there is only maybe 5 or 6 clients that are getting really impacted and the others are not. Let's not worry about the problem too much. The problem is that these 5 people are not getting any throughput. So these 5 people are completely hosed. Even if you feel that this is a small problem, those guys are completely hosed. So you really want to solve the problem for these people. Yeah.
Except for the bursty nature of data, right?
Right. So
they're not. I mean, they're not completely host in the sense like the
not all the
they're
time.
Interfering with are not using the link all the time.
Right. I agree. So of course, if the 2 are not active at the same time, there's no problem. But it's still a problem in general. They can always, sometimes you can have 2 people, using the network at the same time, and you get this very bad performance. So it's still a problem. How important the problem is depends on your volume of traffic and other things. And that's, hard to argue about what user behavior will be like going forward if everybody starts watching video all the time. You cannot really comment on how severe the problem will go. But I think at least the problem exists. So it needs to be examined at least. Okay. So let's look at exposed terminal next. And what we did was the challenge in kind of quantifying how many exposed terminals exist in a real production network is very hard, because everybody does carrier sensing typically. And once you do carrier sensing, you cannot know whether there was an exposed terminal or not. So we had to do the exposed terminal experiments on our testbed. So what we did was we distributed about, I think in this experiment there were 30 nodes. And we kind of treated them as different nodes as client AP pairs. We kind of chose the APs to be the nodes that were closest to the physical APs in the infrastructure, kind of mimicking the behavior of the wireless production network. And here, what the plot shows on the y-axis, x-axis, you have the fraction of links. On the y-axis, you basically have a ratio of throughputs. The ratio is, on the numerator, you have no carrier sensing. That is, if exposed terminals could be exploited. That is, if 2 links could actually transmit, you could transmit. On the denominator, you have carrier sensed throughputs, which means that if exposed terminals could be handled, then you would get the higher throughput, right? Which means that if you look at the line which says 1, which that means anything that is below that or equal to that, those are not really exposed terminals. Anything above that are exposed terminals. Okay? So we have some links that are perfect exposed terminals in our testbed, and essentially if you could handle exposed terminal, you get double the throughput. Okay, so both of these problems exist in one explained through the production WLANs, other in our testbed, but both are at least significant enough that they can allow us to get some gains. Okay, so we believe that there is a lost opportunity here because we could do something by scheduling, and the enterprise wireless LAN environment has some very unique capabilities that allow us to do such scheduling. Okay, so why is that? So imagine that this edge router actually could somehow create this conflict graph, which basically says which links interfere with each other in the enterprise environment. Okay, so it has this image of this conflict graph with itself. And when the packets show up, it looks up its conflict graph, and it knows that if the red and the green packet were to be sent together, they are likely to interfere on the channel. Okay, so this information in somehow was available at the router because it sees the two packets come to it, right? It's the only point through which all the packets go, so it knows this information. But once you send it out to the APs, this information is lost. The APs don't know unless you have told the APs something about what the paths look like. Okay, so what we could potentially do, as a very trivial example, is send out the first packet, the router sends out the first packet, and just holds the second packet by a little bit of time, and then sends a second packet after a delay, that thereby mitigating the entire interference. Okay, very simple idea. And again, this is only possible for the downlink packets, because that's all these packets are going through the single router, and cannot be done for the uplink packets. Okay. So basically what we first did was we went ahead and implemented a simple scheduler for only downlink traffic, and it uses it's a FIFO scheduler, so you want to take the next packet and try to schedule in a conflict-free way based on the conflict map that you have generated. So for conflict map generation, we use the technique that Keshav and his students had designed called SMARTA, and it has some very good properties, allows us to be efficient in terms of detecting these conflicts, and we did this scheduling. So we call this first iteration of the solution deterministic scheduling, or DET. Okay, and here is some initial good news. So if you have two-link hidden terminal topology, and depending on what is your load on the two links, DET can improve on DCF. Okay, so basically x-axis is the load per link, and we are increasing the load. And here in the experiment, what we did was we fixed the data rate to be 6 megabits per second. On the rightmost one, you basically have fully loaded, fully saturated links. Yeah.
So I'm guessing the effectiveness of this depends on carrier sense delays and also the wireline to wireless delay of an AP.
Absolutely, and I'll talk about that too. Yeah. So the good news is that we did some modifications. We optimized the delays on the path. We did some modifications to make the Ethernet driver to the wireless driver path very efficient. It doesn't go through the kernel, so it's like a memory copy, so it reduces the variability and the latency in that path. We, of course, implement our scheduling in the kernel, so it's as optimized as we could do without having a real-time operating system running on these nodes. Okay, and the good news is that DET, which is very simplistic, gives you significant gains in hidden terminals when the two links are highly loaded, which is actually good. Of course, if the link is not saturated, then there is no gains because there is not enough traffic, which is fine. That's not a problem. So in the common case, it's not a problem. In the heavy case, you actually gain. So that's actually where we are doing well. Okay, but the bad news is that now I'm showing the same kind of experiments, but for hidden, exposed, and scenarios which are neither hidden nor exposed. Okay, or basically they're regularly interfering links. So hidden is very easy to gain performance because of this DCF does very badly, right? So it's easy to beat hidden terminals. Exposed terminals, of course, we have not done anything about carrier sensing, so we cannot do anything. We don't gain any performance gains. And then for the non-hidden, non-exposed terminals, it turns out in the high load case, we actually lose a little. And that's precisely because of the scheduling inefficiencies we still have in the system. We could not eliminate everything, and slight delays and slight amount of carrier sensing associated with the delays can destabilize your scheduling scenarios and leads to performance problems. Yeah.
How much would adaptive RTS-CTS turning on would buy you?
Yes, so we actually have experiments which show that there are certain hidden terminals that cannot be solved by RTS-CTS either. And RTS-CTS gives you a significant penalty. So we have numbers I'll show you which shows DCF with RTS-CTS, and our schemes. Now, adaptive RTS-CTS is useful is only if your hidden terminal is showing up now and then. If the hidden terminal persists, adaptive becomes all the time RTS-CTS.
No, by adaptive, I mean you turn it on only when you see hidden terminals for specific client AP links.
True, right? True. But for those links, you always turn it on. Effectively, I mean, so long as you don't move, roughly, right? So adaptive is equal to non-adaptive when the hidden terminal links persist. right? So, and we will have some numbers to show what happens with adaptive, basically RTS, CTS enabled. Yeah.
In this particular case, you are showing that the router did the scheduling.
Oh, so right. So we, I kind of didn't really mention this, but we put a special machine on the path. Yeah. So
if you have more than 2 APs, I saw the efficiency of the system will decrease, right? Because I mean,
everything has to pass through it. So if you imagine this is almost like a little more complex function, but happening at the fast path. If you could implement this at on the line card.
Not the basically machine speed issue. The thing is, I mean, that router cannot issue a packet faster than a wireless basic speed.
So
I mean,
you're right. So basically, one scheduler can handle a certain number of access points, and then you have to get another one. So you have to, if you scale, we could actually do with tens of APs. So we went up to 20 APs. One scheduler was sufficient.
If you're using, let's say, 10 APs, am I right in each AP can at the most get 1/10 of the bandwidth for the normal wireless network? I mean, because otherwise, if you schedule too quick, you still run the risk of.
You're right, but our backplane can be a gigabit Ethernet, 10 gig Ethernet, which is way faster than your wireless link speeds if you think of the nominal rates that you'll actually get.
What I mean is this wireless link, on the wireless link, each packet will occupy a certain slot, right?
Yes,
so
exactly.
For example, each, let's say a kilobyte packet usually will occupy somewhere between 1 millisecond, it depends on what you use.
Exactly. 1 millisecond, 2 milliseconds or less.
Something like that.
Yeah.
And in order to not to conflict, you have to space the packet far enough so that when they send down to different APs, they will have no chance of collision.
Yes,
on
exactly.
The space,
exactly.
Right?
Yeah.
And that means that each of the AP will only be able to handle a downlink bandwidth, which is inverse proportional to the number of AP divided by the wireless capacity.
Well, that'll only be for the conflicting ones, right?
Right. So those
the ones that are on the same channel.
Right.
Yeah, but you need to find which one is conflict.
Yes.
But that's and that's what he's doing, right?
Right. That's exactly what we're doing. So if links are not conflicting, then we just let them go.
That's the ideal solution anyway.
Yeah. Yeah. I mean, you couldn't do better than that anyways, right? Exactly. Okay. So the problem we had were with the exposed and the non-exposed, non-hidden terminal scenarios, and one of the challenges with the exposed terminals is that it's not very easy because one approach to really handle exposed terminals is to disable carrier sensing, and I believe that like the CMAP, there's a work from MIT, I guess, right? The CMAP work kind of proposed disabling carrier sensing in a certain way, and they kind of were not focused on the hidden terminal problem as much. And we feel that it can be very dangerous to completely disable carrier sensing. Okay, so that's why that's one of the problems. And what was that other? Sorry, I missed a slide somehow, which I'll try to find. But there is basically we did this detailed benchmark of where the various delays are on the path between the controller, the access point, and the client. And we basically see all the variability in the order of tens of microseconds to hundreds of microseconds in scheduling decisions. And many of this variability comes from not being able to know when, due to carrier sensing, the packet actually goes out on the medium. And there is also, we need to get a wired acknowledgement. So when the MAC layer ACK comes back to the access point, the scheduler needs to eventually know that this packet got scheduled. So there is other delays that are built in, which makes things very hard. So these are basically the two things that we had to deal with. Okay. So the final design that we kind of moved to, we called it CENTAUR, and it tries to mitigate exposed terminals without disabling carrier sensing. Okay. And what we did was we actually fixed the amount of backoffs, but we allowed scheduling. We kept carrier sensing on. We fixed the amount of backoffs to be the average backoff period that you would use between CW min, so between 0 and CW min. Okay, so half of CW min is what we use, and we schedule in epochs. Okay, so what that means is when I get traffic for a particular access point, I don't immediately decide to send it out. I group traffic in units of time, say 2 milliseconds, 5 milliseconds, or 10 milliseconds, and I basically schedule these epochs at different access points. Okay, and the advantage of scheduling in epochs, which means that your group scheduling a bunch of packets together, is that you really are able to hide a lot of the variability in the downlink, because now the variability becomes much smaller because the epochs are kind of going together, And that really helps us benefit in the exposed terminal case. And one other thing that the epochs really help in terms of exposed terminal is that suppose you want 2 packets to go out on the link at the same time, right? Now suppose one packet just goes out, a little before the other packet, right? The second access point, then if it does carrier sensing, will sense this packet and will not be able to schedule the packet because carrier sensing prevents it from sending. But if you send a bunch of packets together to the 2 access points, then the first packet may happen by going out first. But after that, they will get perfectly synchronized, okay? Because they have these fixed backoffs, and they will, second packet, when they try to carrier sense, both the medium is idle, and they will simultaneously send out packet, and all the packets subsequently will go completely in synchrony to the clients. And then the problem basically kind of be solved because you have achieved the synchronization by allowing the first packet, even though it's offset, go out first. Okay, so that was actually one of the tricks that really helped us in managing exposed terminal. And then we could basically, because we don't disable carrier sensing, we can coexist with uplink traffic. Okay, and we used another trick to coexist with uplink traffic, which is what we call a hybrid data path. Okay, and which is a motivation for our name CENTAUR, which is partly centralized, partly distributed, like partly man, partly horse. So CENTAUR basically has a structure where if you think of this special FIFO scheduling system, what it will do is it will examine the packet and make a decision, is this a hidden terminal or an exposed terminal packet? If yes, schedule. If no, just let it go. Let it go on the DCF. Okay? And that reduces the burden on the scheduler because we don't have to schedule a lot of packets. A lot of packets are probably just non-hidden terminal, non-exposed terminal. So we just let them go on the DCF path. So basically, if you identify from your conflict graph maps which ones are hidden terminal scenarios, which one are exposed terminal scenarios, we'll only schedule those packets and not worry about the rest. And it really simplifies the load on the scheduler. And it's also very intuitive because for problems that DCF can solve, why bother trying to put in all this scheduling mechanism to make it messy? So just simplify the problem and handle only the corner cases which DCF is unable to solve. And that really works quite well. Okay, so now I'll show you a targeted set of experiments that we did to validate that this really is a good idea. So these are 2 plots. So the one on the left side is the exposed only terminal scenario, which means that all our links, we were able to basically create exposed terminals by adding a carefully placed node which will behave as an exposed terminal to that link. Okay, and on the x-axis you have throughput, on the y-axis basically it's a CDF of how many links had the throughput. So the first line over there on the exposed terminal case turns out to be that the very thin red line is a CENTAUR with epochs of 2 milliseconds, okay, which is actually pretty bad. It is the worst performing scenario. And epochs of 2 milliseconds is not good enough for us to actually benefit or to leverage the exposed terminal existence because our scheduling granularity is not small enough. It cannot handle 2 milliseconds. We need to have at least a 5 millisecond granularity so that the synchronization actually kicks in and that gives us the performance gains. Okay, and then basically the black line, the solid black line is DCF. Okay, in this experiment we did not do RTS CTS because RTS CTS doesn't help with exposed terminals, but in the hidden one we did. Okay, and then the next 2 lines, the light red and the deep red line, they are CENTAUR with epoch durations of 5 milliseconds and 10 milliseconds. Okay, so you can see a significant, nearly a factor of 2 throughput gain. This is a purely exposed terminal scenario, and these are I think about 19, a total of 19 nodes all organized so that they're all exposed terminals. So the very construed example just to show that in exposed terminals we get various gains by using a certain epoch duration and with CENTAUR. And then the last dotted line is the ideal case, which means that if you were to disable carrier sensing in absence of anything else, what is the best you could do? So we are kind of approaching the best, so which is pretty good that we get almost a factor of 2 gain in all the links as far as we can tell in the scenarios we've tested. Okay, then you go to the next one, which is a hidden terminal only topology. So all links basically here are hidden terminal, everything's downlink in traffic. And the first line that you should look at is the dark black line, that is DCF. Okay, so what happens in DCF is the hidden terminal, when there are hidden terminals, some links will really suffer. And when some links suffer, basically they don't get to transmit, which means some other links will get to transmit and occupy the channel all the time, right? So there is huge unfairness. Some links get no throughput, others get all the throughput because they see the channel is empty, okay? So you have this distribution where maybe 50% of your links have very little throughput, and about maybe top 20% of your links have all the bandwidth, highly unfair scenario, right? And then the dotted line is RTS CTS, and it has a little bit better. It mitigates some of your hidden terminal problems, but not enough. And it does a little better than DCF. And all our CENTAUR schemes, which are in red, actually is able to equitably distribute the bandwidth across most of the clients that we see. So we have a very nice improvement in throughput, and actually the aggregate throughput is conserved in the two experiments. They're very close to each other. So the big gain in hidden terminals is not that you will get more throughput overall, because finally, so long as your environment is fully utilized, that's the best you can do, but it balances the fairness across both hidden terminal and non-hidden terminal links. So that's what we basically get in this experiment. So it's an initial validation that the mechanisms that we have proposed are achieving the expected gains that we hope. Okay. The next micro benchmark that we did was look at what happens with, so the previous one was only downlink traffic, which was simpler because we are scheduling everything. What happens with uplink traffic in the mix? Okay. So in this example, what we did was we had a pair of hidden terminal links and uplink traffic also operating in that environment. And we did hidden terminal plus unscheduled. Unscheduled is uplink, and exposed terminal with unscheduled. And what you can see is that with DCF, the hidden terminals suffer, the uplink gets a lot of the bandwidth, and with CENTAUR, the throughputs, the hidden terminals are mitigated, and the uplink doesn't suffer. Okay? And in fact, in all our cases, the uplink also gains, because when you mitigate some of the hidden terminal problems, the channel utilization becomes better, and when the channel utilization becomes better, everybody gains, because everybody gets a little more of the channel, because there is less collisions, less losses. Okay? And it happens for both cases. So at least uplink can coexist. So these are the initial micro benchmarks. And then we did a large number of studies on different topologies with different types of traffic. So these were kind of painstakingly done by my students. So I'll go through a few of the slides to explain what happened. So these were experiments on mixed topology. So you had hidden terminals, exposed terminal, regular nodes, all of that. And the topmost set of bars basically have DCF, CENTAUR with 2 milliseconds, CENTAUR with 10 milliseconds, and each bar corresponds to a client. There were 9 APs and 12 clients, so each bar is a client, and you have variances and all of that. The high-level bit, so the top-level set of bars is UDP, then you have TCP, then you have delay, not just throughput. So throughputs and then delay. And in general, we improve across all of the cases. Just looking at the first set, you can see that the average aggregate throughput gain across the entire network is about 46%. And the biggest gains, of course, come to the hidden terminals in that case, 1.8 times of their DCF performance. And exposed terminals also get a more than 50% gain in many cases. So overall, in a mixed topology, we perform pretty well. There is a bunch of other experiments. I won't go through all of them. It shows what happens when you have a mix of uplink and downlink, and you change the ratio of the uplink to the downlink. So the gains are kind of persistent across all the scenarios when we varied the amount of uplink and downlink. Okay. In the previous set of results, I say, yeah, go ahead.
Was rate adaptation on or off?
Here. So in the previous set of experiments, we did fixed rate just because it's easy to interpret the results. So we did also different rates, and then we did auto rate, and the gains persist. And the higher the rates, and auto rate actually is even more beneficial to us, because we are operating on larger blocks, and so long as we can predict how things are behaving, we are estimating the delays on the paths, we can actually schedule things pretty well. Whereas DCF goes into rate adaptation. With hidden terminals, things get very bad with rate adaptation, because it's really not the rate which is the problem, but the hidden terminal which is the problem. So auto rate actually makes it even better for us, okay? Because rate is not the problem when there are hidden terminals. That's really the high-level thing. So we have experiments. Now, this was another interesting experiment, which is basically playing back real traces on the same network. So what we did was we took the SIGCOMP 2004 traces, which were a bunch of web downloads people were doing, and we played them back from the clients, and which, of course, clients send request, data comes back. And this plot shows a distribution of delays in downloading that web pages or whatever they were for all the different sessions that were run, and sorted by the transaction size of the file that was being fetched. And basically, we get delay gains over the fetch durations for each of these web downloads. We did more experiments with VoIP traffic, looking at mean opinion score and so on, and all of them were pretty good. So overall, based on the amount of experiments we have done, we feel that this is a fairly robust solution for an enterprise setting because it doesn't hurt people who are non-hidden, non-exposed, and it really gains when they're hidden and exposed. So overall, we don't lose much, but we gain a lot. So it's kind of a solution that we're very comfortable with in kind of proposing for an enterprise environment. And the advantage here is that we don't require any client level modification. Everything, any change that we have done is only at the access point and the controller side, nothing. And the access point is really, in fact, access point, the only change we made was the driver to driver path optimization, which is a serious change in terms of amount of coding effort, but it's really trying to optimize the path latencies. Okay, and that was more important when we were doing deterministic scheduling. It became less important when we do epoch-based scheduling because we can live with variabilities better. So in fact, I think if we just disable the changes we made in the access point, we should be still fine. There are other parameter changes in the access point, which is the fixed backoffs, which is a parameter choice that we had made, and so on. But anyways, the clients don't change, and that's, I think, the biggest advantage in this whole story. Yeah.
I noticed. This scheduling seems effective in enterprise scenarios.
Mm-hmm.
How about home scenarios?
Right,
even at my home, I store multiple APs from my neighbors.
Right. So, very good question. So, what happens in home scenarios? Do the result translate to home scenarios? And the challenge there is that you don't have a controller that can manage all your access points of different homes, right? If you could, then you could just translate the same results to the home environment, but I don't know if that is an easy fix because your neighbor may be actually operating using a different ISP, and would you allow scheduling at that level from a controller to all the ISPs networks? That's really the key. Yeah.
Is your department not running 11A?
Our department has 11A, but very few clients on it. Yeah.
It's really, A is just dying out. People seem to be really concerned about range, and it's just dying out. It seems like, in a dense environment, low range is a blessing and not a problem. But it's hard to now even go to Fry's and try to buy 11A AP and
I don't understand, because in this building we've got hundreds of access. If you sit in the atrium, it's ridiculous how many APs you hear.
Yeah,
exactly. So I guess it could solve the problem, but that's not true.
Well, I'm just wondering,
12 channels.
Like the terminals exposed.
But there is actually another motivation why you may want to keep a bunch of APs in the same channel, which is because of handoffs. So if you actually keep APs in the same channel and they have overlap, then the handoff process becomes smooth because the client doesn't have to change channels for handoff. So there is some reason why people may, even if you use 11A, there may be some reason why you may want to deploy things to be on the same channel.
Even today, when you change from moving from one access point to the other, even if you're using the same channel, I assume the process isn't that smooth, right?
it's pretty smooth.
Pretty smooth? Okay.
Yeah, but with VoIP, the smooth will be not as smooth depending on what. Yeah.
What's the complexity of gathering the conflict map?
So the complexity is really, so the conflict map requires the APs to be able to send packets in a synchronized way and observe whether responses come back or not. And that's really not our work, so I didn't go into the details. But basically, if you send 2 packets and you don't get the ACKs back, and you do this a couple of times, you know that there is some sort of conflict. And based on what kind of experiment you do, you can tell which kind of conflict it is.
But you do it for like
individual packets.
No, but you do it for every AP pair and client pair?
Every AP pair and client pair. And actually for a 10 AP network with 12 clients or 9 AP network with 12 clients, at least the smartest scheme can achieve this within, let's say, 4 or 5 seconds. And you can probably distribute it. It doesn't have to be done continuously, so you can space it out. That was basic. All this is factored into the experiment. So there is some.
The complexity versus performance. The performance benefits seem useful. Just
there is complexity in the detecting the interference, and I think the complexity in scheduling is there. So if you have very inaccurate scheduling, you will get bad measurements basically. But
so here's the other thing. I mean, since you have the central controller for the AP, if you detect that there are these hidden terminal situations, or if you suspect that they might occur, you might as well change the AP channel assignment.
So the problem is that these are maybe transient, right? It could be just two clients sitting at some location that is causing this, but most of the time it just doesn't exist. And you could say that, do we change it for these two clients when there are 20 other clients that will get affected when each?
That's okay, right? That's fine. Aruba already does dynamic channel assignment.
Aruba does?
Yeah, well, you know how dynamic Aruba is? Once every night.
Sure, but
so. But I mean, you can do.
But that's an
also,
interesting
right?
idea. Yeah.
You can force the AP to disassociate. So let's say there are two clients. You force one client to just disassociate.
Sure.
So it will be, let it associate only with other AP.
That's a solution. Sure. I mean, whether by changing channel do you introduce? I mean, maybe you kind of loop around. There's another hidden terminal somewhere else.
No, don't change channels. Force the client to go on another channel. Disassociate him.
What if that is only AP for that client? I mean, you could get into corner cases. I guess you're right that we could do some of the other things too. I agree, but we haven't investigated that. You guys are looking at that, so certainly you should tell us what happens. Okay. Yeah. So okay. So I was told I have until 12, so I have many more slides to go. Is that right?
Yeah.
Okay.
Too much into the lunch time, but that's okay.
So I was told I have until 12, which is how I have planned to talk. If you want, I can speed up and talk about a few less things. Okay. So with that, I'll kind of move on to the next question, which is how do we leverage the infrastructure to improve energy of mobile devices? And here, basically, we start okay. So let me just. I think this. Never mind. Yeah, so basically the approach we are trying to take is, packet losses are wasteful. We want to reduce them, avoid them as much as possible. And then if possible, we also want to improve the efficiency of each transmitted bit. So I'll try to talk about both of them in some amount. So the fundamental problem of, packet loss, rate adaptation, congestion window adaptation, all of these things is the ability to figure out what caused a packet loss, right? So imagine this scenario. Transmitter sends a packet to the receiver. Packet is received in error, and then the error could have happened due to at least two different reasons. It could be a collision or a weak signal. And the interesting thing is each scenario requires a different form of adaptation. So if you have a weak signal and you do RTS CTS, or you do back off, you do adaptive RTS CTS or anything, that's the wrong solution. What you need to do is you need to either reduce the data rate or increase the transmit power. Okay? Whereas if it's a collision and you reduce the data rate, you're actually making the problem worse. And typically most systems tend to do both because they don't know which one it is. So they do both, and one of them at least is wrong, right? So the fundamental question I think in our mind is, how can we distinguish between what is the cause of a packet loss? Was it a weak signal or was it a collision? Okay, so that's the first thing that we wanted to solve, and then we'll show how to utilize that information in an infrastructure-based system. So we took a very simple approach, and almost like a brain-dead approach in my opinion, but it actually works pretty well, so it's worth talking about it. So let's imagine that we send this packet, transmitted packet, and it's received at the particular receiver, and it may be received in error. Okay, so the question we posed is, by conducting like a post-mortem of this packet, can we tell what is the cause of the error, whether it's collision or weak signal? Okay, so now imagine that if you have the original transmitted packet and the received packet in error, you could compare things like which bits were in error and what can you tell from these different bits. Okay, so we can create an error bitmap. But the only way you could do this is if you allow the received packet in error to be sent back to the source. Okay, so we took this kind of a simple approach and said that, okay, we'll send a packet. If the packet is received in error, we'll send the corrupt packet back to the source. Okay, and then we'll let the source figure out what happened, and then based on that, it'll do the right thing in terms of rate adaptation or whatever, congestion window adaptation and other things like that. Now, this may seem like a bad idea because you're wasting bandwidth in just sending this big corrupt packet back. But from the energy point of view, if you think about it, most of your, the energy savings that we really want are at the clients. Okay, so what we do is we do this for client traffic. So that is, client sending packets to the access points. Only the access point sends this packet back. And of course, there is reception cost at the client, but that is probably much less than transmitted cost. So that's fine. So for downlink traffic, we don't do this. Okay, this is only for uplink traffic.
But it's not in at least current hardware. Receive cost is pretty much equal to transmit cost.
Okay, that's. It depends on the card, but so okay. So I agree that maybe there is some increased cost, but I think the overall gains that we'll get actually, far out.
Can you just use the receiving SNR at the AP side to figure out?
Receiving SNR doesn't give you enough information. I guess with SDR kind of things, you could probably look at more information in the packet and figure this out. But we don't do this. We are doing this on 802.11. Okay, if you could look at received SNR on packet chunks and things like that, you could kind of tell. Okay, so this work is actually very. I don't think we have gone deep enough into the problem, but we have taken some very initial steps. But I'll present some results on that. So we actually kind of were trying to look at 802.11 level metrics, which we could observe by observing bit error patterns in the packet and by knowing which bits map to which symbols and things like that. Okay, so we basically looked at receive signal strength. We looked at bit error rate. We looked at what we call errors per symbol. So how many bits were in error per individual symbol? What is the symbol error rate, which is basically how many symbols were in error as opposed to bits in error. And then we computed what we call the S-score, which is the number of consecutive symbols in error. Okay, so you get a high S-score if you have more number of consecutive symbols in error as opposed to they're equally sparse, spread out through the packet. Okay, so we could compute all of them, and basically the high-level intuition is that if there is a collision, and similar ideas now, of course, have been proposed by others when they did things like analog network coding, where they were trying to observe where a packet actually starts colliding and things like that. But by looking at much more detailed information in the packet, we are actually doing this through 802.11 only. And we basically expect that if there is a collision, a lot of bit errors will happen in a large number within the two packets. We expect that the errors per symbol will go up. Which symbols go in error? They actually have a lot of errors. These were some of the intuition that we had. And then the number of consecutive symbols in error will also go up because of the same effect that you have in the bit errors and so on. So we looked at all these 5 different metrics. Okay, and the overall system that what we designed was we took these 5 metrics, and when the client sends a packet, the AP sends the error packet back to the client. It looks at the error bit map, and it computes all these different metrics. And all these metrics basically vote and say, yeah, it's a collision or it's a weak signal. And based on that, we do link adaptation. Okay, a very simple algorithm. It has some overheads, but that's what we did. And what's interesting is that actually each of these metrics have some ability to discern between collision and weak signal. It's not perfect. Yeah.
So when you say weak signal, you mean low SNR, right?
Low SNR.
So does low SNR also mean that the signal is low, or does it mean the noise is high?
It could be either.
But if the noise is high, it could be because of collision?
The noise is high. I could not tell, at least. I don't know. I mean, it could be, but it's.
I'm just wondering what the sort of difference between the two is. I mean, isn't.
So you could. So basically, the RSS, receive signal strength measure that we get from the card doesn't tell us which of the two actually happens.
Right, I'm just talking in a theoretical way. I'm just curious, what does it mean to have a collision with high SNR versus a low SNR? I'm not sure what that means.
I think that it is like synchronization got lost, and whether, I don't know.
I think about this way. I mean, if it's collision, right, I assume one of the packets, you probably will see the packet header in clear. Because collision is caused by 2 different packet sources. So you have, one packet goes through the other, basically part of the packet get collide with another packet, and so get mixed. If it's weak signal, the general definition I would say signal to noise ratio is low.
Right,
and
but
can
signal to
cause-
noise ratio can be low because either the signal is low
or
or the
even
noise is
noise,
high.
or for
Yes.
example, let's say microwave temperature up.
Right,
I mean,
but noise is high means collision, right?
yeah,
Could
no,
mean collision.
So what I'm basically thinking is this: you can define noise as high as this. If the noise is really that high, it should wipe out the whole packet. So I mean, you probably will basically. I mean,
Okay, well, let's talk about 1 bit.
okay.
For a given bit, what's the definition of collision versus low signal?
I guess for this particular bit, I cannot figure out. Because you don't know whether the noise is from another source or it's just from some other unintended protocol. I mean, or let's say this, collision is defined as the client, I mean the source is another client, speaking of also 802.11 language, right? Weak signal, I mean where the source can be, let's say, basically a cordless phone or microwave or whatever, which just emits signal, not in your language.
So
Is it possible to get these?
Another way to put what probably Jin is getting at is that if it's because of a collision, the increase in noise at the receiver is temporary, and in the sense it does not overlap the entire packet.
Right. So, but I'm talking about that part I got from
Right.
bracketer. I'm just curious about a 1 bit. Is it possible to tell whether do you only get SNR measure or do you get some signal measure? I mean, remember the stuff you were doing with Lily,
Yeah.
that the noise can be sometimes additive versus the signal can be sometimes additive. I'm just curious whether you get an indication from the card that tells you.
From the card?
card doesn't.
Do you only get SNR or do you get signal
You
and
get-
noise?
you
If
actually
got
get
those two terms,
S
you'll be
plus
able to
I,
tell, right?
don't you?
There's no way.
There is no way to do that.
I
Right.
mean, the
I mean,
card
otherwise-
usually doesn't tell
I
you,
think
but
it's separate
I mean,
noise.
Yeah, yeah.
potentially you can get extract signal, I mean, from the card, it's a signal strength level. I mean, it depends, I mean, whether the chip is willing to give you that information.
I don't think it even gives you S and N separately. Sometimes it gives S plus I, right?
No, well, so you can get N because the hardware knows baseline N.
Okay,
That's
sure.
what it
Yeah.
used to synchronize
Yeah.
itself and gain control
That's
and
true.
things like that. But I think what's unclear is like what time frame it is actually.
That's another problem. Average
Plus, like, so the interesting thing is like people now have done really detailed measurements where actually like, so instead of the reason RSS is not predictable is because of OFDM. What really matters is like SNR of individual subcarriers.
Yes,
And that
that's
can be variable. And what the card gives you is some kind of average measure
Average.
across subcarriers.
Sure.
So what's really predictive, it's kind of like going back to the underlying physics, what's really predictive of performance is like the SNR of individual subcarriers.
Sure.
So if you knew that, then your prediction would be a lot more accurate.
That's absolutely right. I agree.
Yeah.
So we did this about in 2007, 2008 time frame.
The reason the SNR of individual subcarriers is not, the average differs significantly from sort of the, because there is a high variance and the reason.
Selective fading,
And,
essentially.
I see, it is selective fading or is it collision?
No, it's selective fading. Yeah.
But if it's collision, it probably will affect a lot of them in the same way.
Because different subcarrier frequencies,
They're pretty close, right? I mean, they're not that different.
well, it does matter, it turns out, which is the primary motivation behind OFDM as well. So I think in measurements you can see like
Yeah.
certain subs.
I see what you're saying. They're deliberately selected so that they have differential fading.
Or being deliberately
Or,
selective.
okay. I mean, you want to get some. Anyway.
So actually, I'll kind of interest of time, I'll summarize some of the main results that we had. So it turns out that by using this voting scheme, what we could actually do was we could get a very accurate prediction of when the collision happens due to a weak signal. So we got very high accuracy. If it was a weak signal based collision, weak signal based packet loss, we could tell it pretty accurately. But if it was a collision based packet loss, we would make a incorrect prediction about 40% of the time. Okay, so we have one side we could do accurately, the other side we couldn't. That was basically what this set of observations, the set of metrics we defined. So clearly there is scope for improvement, and some of the things that Rutul is mentioning, looking at individual OFDM, subcarriers probably will give you much better performance, but this was the first stab at the problem. So,
In this case, I mean, when you talk about the accuracy, how do you know the ground truth?
right, so we create the ground truth. So what we did was we position nodes in a way that we know that there is no other interfering source, and so it has to be weak signal and so on. Yeah, so ground truth is created for us. So one of the problems that we faced in kind of figuring out why detecting weak signal was a problem was, given the metrics that we chose, capture effect came and really interfered with us. If capture effect happened, we couldn't tell if the packet was lost due to weak signal versus collision. Okay, and the other thing that really messed up our measurements or our predictability of the metrics was the relative size of the colliding packets. If there is a small packet colliding with a large packet, that looked differently than a big packet, two big packets colliding with each other. These were some problems. But anyway, so we went and implemented the system with all the overheads of sending the corrupt packet back and all of that. And essentially, this is basically showing over time throughput gains, which also translates. So you can translate that to energy per bit to kind of translate the energy gains. And so we implemented this system called COLLIE, which stands for the Collision Inferencing Engine in the hardware. Sorry, in the system, not hardware, in the kernel. And this is over time the throughput you get for a mobile client in presence of other traffic. This is basically because you're able to detect which of the two is happening to some level of accuracy and take corrective measures better in each of these two.
How do you translate throughput to energy?
So this is so we divide the throughput by the total amount of energy consumed, and I'll show. I think I have the energy numbers in the subsequent plot. Where did we have it? Oh, I think that's not throughput by energy actually. These are throughput gains, and I think I don't have the energy plots here actually. You're right.
But you actually measure energy?
We actually measure energy. We have energy measurements just by taking the amount of energy consumed across the card. And I think the slide that at least illustrates the point is that the number of retransmissions with COLLIE goes down significantly. So that will already give you significant energy gains. So reduction in wasted retransmission goes down by 40%. Okay, so I mean it depends on how much mobility, how much interference, all of that. So if it's a very good channel, it doesn't matter. So, yeah. And some of these measurements were done by emulating this on a SPH 101 voice over Wi-Fi phone. So we were trying to basically emulate this for a voice over Wi-Fi device. Okay, so I think I'll just talk about one more thing. I'll skip over a bunch of slides, so just pardon me here. So this is basically, there's some work we did on kind of reducing or improving the efficiency of the number of bits you transmit. It is, the initial part is header compression, but there is a lot of interesting other ways of eliminating redundancy. You could eliminate a bunch of control messages that are redundant. You could eliminate redundancy in payloads. So there is, the one I'm skipping over is probably some people here have heard of it. This is our authentication work using radiometric fingerprinting, which is basically, I don't know, this is a Mobicom paper from last year, which basically looking at specific hardware level characteristics in packets, or rather manifestation of hardware level transmitter properties in the packets in terms of distorted frequencies or let me just get, this is our, yeah. So looking at things like phase error, the sync correlation error in the received packets, can you tell different transmitters apart, and then can you build security based on this kind of feature? So this work was done using a very sophisticated piece of hardware, a vector signal analyzer that would observe the packets, calculate this metrics, give it out, and then we feed it into a machine learning tool, and we could show really high gains in terms of performance in accurately determining transmitters without requiring clients to authenticate. Okay. So I'm going to skip over this because I want to talk about the one last thing, which is one of our most recent work, and I'm going to talk about for a couple of minutes probably. So we have been looking at this problem of Wi-Fi video multicast, and yeah.
Can I suggest something? Why don't you do you're going to be here for the rest of the week, right?
Right, sure.
Why don't we do a full talk on this?
Okay, this one you mean?
Yeah.
Okay.
If it's okay with you, I would actually like to hear more about it. This
No
is just
problem,
my
no
preference.
problem. I mean,
Can I hear a 2-minute version in case I can?
Well, this 2-minute version is really focusing on the problem and the results, and maybe we can talk about this informally, and maybe that's fine. Yeah. So basically, the problem we were looking at kind of was motivated by something that our campus IT folks came and talked to us, and they said that they are interested in doing this campus-wide broadcast of lectures, and they feel that in many cases students sit together in a library or in a dorm, and they will be associated to the same access point. And if you broadcast the same content to all the users, it's going to self-interfere, and it's going to be a lot of problems, especially if you go towards HD quality video. So how can we sustain high quality video over multiple users when the video content is the same? So this is basically Wi-Fi video multicast. And in this 2-minute teaser, I'm only going to give you the results and not the techniques, but we can talk offline. So basically, I think the punchline for our work really was that we could scale up to 25 users when we were transmitting video at the rate of 20 megabits per second, which I thought was very impressive. And here is one experiment where it shows a few of the interesting things. So this is PSNR of a video clip at the 20 megabit per second rate, and we had clients that were located in the good, medium, and bad channel conditions of receiving the same content. And we have 4 sets of bars for each client. So the first, the black one, is unicast simultaneously. So it's individual unicast to each particular user, 10 of them in this case. And obviously, 20 times 10 is 200 megabits per second. So of course, you don't get any useful PSNR over here. So the black line is very bad. The next one is the red line, which is broadcast, and broadcast at the best possible data rate that you could pick. A single rate, fixed rate, but the best possible rate. And it does well because you're only transmitting one stream, but whoever doesn't get it, doesn't get it. Okay? The next one, the green, is individual unicast. So this is actually interesting. Individual unicast is you're only transmitting to one user at a time, and there is no other user that is receiving stream at that time. Okay? So individual unicast, you expect it to do very well because there's only one user. But the funny thing that happens is that when the channel is good, or for the users for whom the channel is good, you get very good performance. As you get from medium to worse, individual unicast starts performing badly, especially when compared to our scheme, which we call Medusa. Okay? And the interesting aspect about individual unicast is that here what happens is there is some notion of head of line blocking that happens. So if the channel is bad, and suppose you have a P packet that is sitting in the Wi-Fi card's buffer, and it's trying to transmit this, and it's not going through, it keeps on transmitting this until it succeeds, and it keeps on transmitting more P frames until they succeed, and then the I frame tries to go up, but the I frame can get delayed sufficiently that the P and the B frames are occupying more of the channel time in some cases. In Medusa, what happens is we, at the proxy, are deciding how to retransmit and what to retransmit. Okay, we are not letting the MAC layer do anything because we are doing broadcast. In broadcast, we don't have any acknowledgement, so we cannot retransmit. So because we are able to kind of expose packet priority, or even the retransmission priority, which packet is more important to retransmit than others, and how do you construct the correct schedule of packets to transmit, we are actually able to implement a better schedule of transmissions because we are kind of aware of packet priority. So we actually, even in the bad case, we outperform unicast to individual clients, which was a very interesting result from our point of view, that we can get to this kind of performance. The scheme is actually fairly adaptive, and so we have a bunch of packet priority mechanisms in there. We have rate adaptation for broadcast packets. We have a scheduling mechanism, and the rate adaptation has a little bit of interesting complexity where we set up a base rate to use for each base rate to use for the entire group, and then we have mechanisms to choose data rates for different packets, which is above the base rate in certain cases, depending on the packet priority. Okay? And here is some examples showing impact of things like interference on performance. So we started a interfering source, and it shows that broadcast, of course, doesn't do very well. Individual unicast in general does well, and we can also kind of get to the same rate. Our latency in adapting the rate is a little slower because we are trying to do it for the whole group, and so we are a little bit conservative compared to the most efficient way of doing it a single user, but it is not significant. And we did similar mobility experiments. So one user kind of went behind a wall and came back in a few seconds quickly, and we looked at how adaptive things are. So it's kind of a interesting solution of trying to do HD video to a bunch of users. So I'll be happy to talk about more details maybe subsequently with each of you. So I think that kind of summarizes our work. There is a bunch of other projects in our group we do. We're looking at this metro scale mesh network management with a 250 node access point network that we have in downtown Madison, and we're looking at some of the issues of fault management there. It's kind of slowed down a little bit. We need to pick up the pace there. And the last thing I'll mention in the context of video services over wireless networks, this is another piece of, I think, very interesting work. But this is one example where we are looking at using SDRs for exploiting application layer information with the file layer encoding that is employed. Okay, so we call it approximate communication. And the high-level idea is that if you think of a set of, you think of any constellation scheme, like 256 or 16 or 64 QAM, when a packet or when a symbol is transmitted, so there is a probability the symbol will be received in error. And the symbol error probability kind of decays with distance from the location of the transmitted symbol, that is in the IQ space. So you are likely to make errors which are close to you in the IQ space than which are far away from you. And the reason that will happen is if you're selecting a good enough rate, you will obviously be making, most of the times you will be correct. Otherwise, you're not going to use that rate. When you rate adapt, you make sure that errors are close by, or in fact, you're trying to make sure that most of the times you're getting the right symbol. So as a natural consequence, errors are also close by more than they are far away. Okay? So because of this property, what we can actually do is, if you think of a symbol constituting of a number of bits, we can selectively provide greater priority, or the channel, I should say, the channel provides greater protection to some bits than others. So effectively, in 6 bits of a 64 QAM, let's say the first 2 bits are the most protected, next 2 bits are a little less, and the last 2 are even less. So if you can now map I, P, and B frames to the most protected, least protected bit positions, then overall the channel is giving you differential error protection for free without even having to introduce AFECs or anything like that. So you can do much more on top of that, but this is some capability that the channel already provides, and we never exploit it. Okay? So that's the basis of approximate communication. So we designed a system based on this using the warp radios from Rice University. There is feedback and all of that. So it does change the underlying MAC protocol and so on. And there are lots of experimental results we have done to show how this works. Yeah.
So you're saying in a given symbol,
Yes.
Bit errors are differential?
Yes. Depending on the bit position and depending on the encoding scheme that you use. So encoding scheme says how you map bits.
Right, so why I mean, I would have thought like the coding scheme would be, optimal in the sense like all other possible symbols are equally distant from a valid symbol.
But that's not possible, right? Because if you take any position in the 64 QAM,
yeah,
there are 63 other positions. How can you ensure that they're all equally likely?
But no, you care about the symbols around a particular symbol,
right?
There are equal number of symbols around a particular symbol,
right?
And aren't they distant?
All of those are probably equally likely. I agree. Yeah. But you can still ensure that in general, depending on how you map bit values to symbols, you can ensure that the first bit is the most protected, that the likelihood of the first bit error, it depends on how many times by going to the neighboring symbol you flip that bit. Right. And that can be made fewer than the last bit flipping when you go across one symbol. So that's by choosing the encoding scheme.
I agree, by design that can be made fewer, but is that the property of current codes that are being used?
Some current codes actually have that property, but you can also select the mapping. It's a choice that you can make, right? It's a completely software decision.
You create different priority in the bits. So I mean that depends on what information you want to expose to that relay. In the general basic protocol, you just assume each bit is equally important.
Well, yeah. So at the high layers, yeah. Well, I guess for some reason I assume that the modulation, the coding being used in modulation is like you'll design it in a way that's not biased or optimized.
Right. So what people do is they have this scrambler module in the middle, and that tries to kind of randomly throw around the bits so that the bits that you send get mapped randomly to this position so that all bits in some ways are equally likely to be in error because you have introduced some redundancies. But even after scrambling, the bit positions are in error. Different bit positions have different error. So if you scramble the I frame and you scramble the P frame and you scramble the B frame, and then you take the scramble bits and put it on the most protected, medium protected, least protected, you get that kind of property for the I bits, which are scrambled P bits. So overall, you get this differential protection for free. And that's what you can exploit. And then you can, so we're looking at various follow-up problems, which is how do you choose a constellation space that has certain properties of protection and things like that, or what are better mappings between the encoding scheme that you use for the result. So we got, there's a lot, this is one slide for a whole paper actually, but we can talk about.
Because you mixed various frames within the same packet.
That is true. That is true.
It's different solution.
Yes.
Different solution.
Yeah, it's a different, this is a single unicast problem that we're looking at, sure. And it really, what it does is in fact, what it really does is for a symbol that is in error, if you think of schemes like, blanking out, I think zigzag or MRD and its variant, soft, all of these. What they're trying to do is they're trying to increase the probability that the symbol is correctly decoded. What we are trying to do is even if the symbol is decoded in error, we will extract a few good bits out of it. So we are still extracting more out of the symbols which are in error, and that's what Apex, the system is called Apex. That's what it does. But it of course requests changes both sides, MAC5 and stuff like that. So I'll stop there. I think there's a lot of things condensed in, and I probably skipped over a bunch of things, but hopefully it sets up some context for more conversations. Thank you.